good morning. Welcome you all to this NPTEL course on electrical distribution system analysis. And today we will focus on the distribution system protection issues, especially due to integration of distributed generations. Now, due to the advancement in power electronics, enhanced feasibility of small scale power generations, also known as micro resources or distributed energy resources, so called DRs, transition from limited use in emergency backups and rural areas to significant roles in power generation, rise of distributed generations, that is widespread distribution of DR leading to the concept of DGs, increasing integration of DG as an alternative to expensive network expansions, benefit for consumers and power grids alongside new challenges in protection and control. There are serious challenges to protection systems because of introducing DGs in distribution system. DG's negative effect on short circuit current and overcurrent protection systems. Issues like altered fault current flows, protection system blindness, and disrupted coordination between protective devices become an issue. Now, to start with, before we get into protection issues, let us understand the simple short circuit analysis. Now, considering the RL series circuit with a load connected, the moment your switch is closed and exposed to a voltage of Vs, using differential equation, the steady state AC short circuit current, which is given by IAC, that is Vs upon R times 1 minus e to power minus t by tau. The tau, which is L upon R, which is XL upon omega R. Capacitors and inductors store energy in the networks, which when discharged during fault increases the short circuit current, and this increase is known as DC fault component and given by IDC, which is I naught times e to power minus t by tau. And you could see the DC offset from the characteristic, and we can have the AC symmetrical component and total fault current asymmetrical, which is given by the summation of the AC component plus the DC component, which is given by Vs upon R plus I naught minus Vs upon R e to power minus t by tau. So, the asymmetrical fault current, which is the summation of the DC components as well as the AC component, and which is shown in the green characteristic to be considered as my IF. Now, synchronous machine based distributed generations. Now, when a synchronous machine experiences a short circuit at its terminal, the initial current is extremely high, eventually settling to a steady state level. Typically, synchronous machines produce a current about 6 times their rated level for a few cycles. Then it decreases to 200 to 400% of the rated current, excluding DC offset. The continuous flow of short circuit current in the circuit leads to a rise in winding temperature, which in turn increases the machine's impedance. The increased impedance accelerates the decay of the AC envelope, as you could see from the diagram. Industries have defined 3 types of reactances, that is subtransient, transient and synchronous reactances. Now, let us focus on the behavior of induction machine based DGs. In the event of a short circuit at an induction machine terminal, the current initially spikes significantly before eventually dropping off entirely. During this phase, induction machine typically output a current approximately 6 times their rated capacity. This fault behavior is caused by the motor's inertia interacting with the field flux, which is induced by the stator. Under steady state fault conditions, the transient and synchronous reactances values effectively become infinite. As a result, only a subtransient reactance value is attributed to induction machines. This assigned value is higher than the locked rotor reactance and is adjusted to reflect the diminishing contribution of the motor current to the fault. Now, moving to inverter based DGs, inverters differ dynamically from synchronous or induction machine as they lack a rotating mass component and thus do not develop inertia to carry fault current based on electromagnetic characteristics. Powertronics inverters exhibits a faster decaying fault current envelope due to the absence of the predominantly inductive traits found in rotating machines, influencing the constants of the circuits. Inverters offer unique control capabilities, allowing for programmable responses to fault conditions, which affect the fault current characteristics. In the DC-AC converter, the DC link capacitor maintains near constant voltage during transients, with the voltage control scheme showing higher initial current overshoot compared to the slower rise and fall of the current control scheme. During transient period, first 5 to 10 cycles, the DER under a voltage control scheme will contribute higher fault currents. Advanced Powertronic interface systems have the potential to use fast subcycle semiconductor switches for reducing negative impact of DER systems. An early study in the year actually 1985-1986 with 30 PV sources and 2 kilowatt inverters as an example on a 13.8 kV feeder showed inverter contributed less than double their peak current to fault for under 200 microseconds. So this was the initial study as they shut off within half a cycle post fault inception, rendering their impact on fault current negligible. Further analysis of 3 megawatt DG unit indicated minimal impact on the fault current. Another research highlighted that inverter based DG unit with low impedance connections to the grid have negligible fault current contributions, but high impedance connections significantly increase this contribution, affecting fuse coordination with increased DG penetration. A different study categorized 6 inverters based on disconnection speeds, some disconnecting in less than one cycle post fault with almost zero fault current contribution, and other disconnecting after several cycles up to 10 with minimal contribution and varying fault current waveforms. According to IEEE standards, PV units with inverter terminal voltage under 0.5 per unit disconnect in less than 6 cycles, rendering their fault current contribution negligible for higher voltages. The contribution can affect fault current, potentially taking up to 120 cycles for disconnection. The fault contribution of PV inverters generally does not surpass 120% of their rated current. To summarize, inverter based DG units fault current contribution usually stays below 200% of their rated current. Now, what are the impact of a distributed generation on a radial distribution system? I request all of you to focus on the diagram ABCD, which has been given in the left half of the slide. Now, let us focus on, we have taken a radial distribution network, and a radial network that demonstrates the integration of a 1.5 megawatt synchronous DG unit alter the short circuit current at different network locations. So, by placing the DG at different location, we'll see how does it affect the short circuit currents. Now, influenced by the DG's connection point to the grid and the fault location. First of all, consider the figure A in a network without any DG. So, you don't have any DG, it's a simple network. Figure number A, fault current through reclosures RC1 and RC2 are identical for a fault at the feeder marked X. Now, if you add a distributed generation, okay, after the RC1 of the figure B, reduces the fault current IS, and increase the fault current through RC2. Okay, because of this, that will reduce your IS and increase the fault current through RC2. Now, if you relocating the DG connection to a point after RC2 instead of after RC1, if you bring to a point after RC2, which is shown in figure C, decreases the fault current through both RC1 as well as RC2. Now, with the DG placed after RC2 and the fault occurring on the lateral feeder, that means this point, that is shown in figure D, the fault current IS diminishes and the current through RC2 reverse its direction. If the fault current IR exceeds, if this IR exceeds the RC2 setting, then the recloser will trip for certain, cutting off power, which poses a problem for a protection system. So, what we are going to highlight here, if the distribution generations are not there, then we have a classical protection setting mechanism. But once we place the DG, and depending upon its location, which may force you to change your existing protection mechanism to accommodate distributed generations in the system. Now, impact of distributed generations on recloser fuse coordination, which is a very interesting one. Now, connecting a DG unit after recloser, as shown in the figure, influences the fault current passing through the recloser. Now, in case where a fault current on the tap line and the DG has substantial capacity, the fault current through the fuse might exceed that through the recloser, which is certain. As shown in figure number B, the situation is exacerbated when several DG units are connected to downstream feeders, increasing the fault current imbalance. Instead of one, you take multiple ones. The distance between the interconnected DG unit and the fault location also affect the fault current experienced by both the recloser and the fuse, with greater distance leading to a decreased fault current at the recloser. The use of DG unit with synchronous generator leads to a more significant change in fault level compared to inverter based DG units, which have a minimal impact on short circuit current and its duration. Now, we'll also focus on how does it impact the DG on multiple distributed feeders. Now, we have actually multiple feeders, that is feeder number 1, feeder number 2, we have a generator Y1, we have a generator Y2. In network where multiple distribution feeders are connected in parallel, that is feeder 1 and feeder 2, to sub-transmission substations, a DG unit on one feeder impact the fault current through the upstream circuit breaker CB and fuses on parallel feeders. As shown in the figure left to us, for a fault on feeder 1, Y2 DG2 on feeder 2 can increase the fault current through CB3, exceeding the short circuit current through the main grid side CB1. The introduction of DG2 on feeder 2 decreases the fault current through the main CB1 while increasing its through CV3 or the fuse, concurrently the presence of Y1 on feeder 1 can further reduce the fault current through grid side CB1. The fault current seen by the CB2 fuse 2 depends on DG2 size on the feeder 2, and with a large DG1 leading to a smaller fault current through CB2 or fuse 2. That means in case of multiple distribution feeders, if you have multiple DGs in each feeder, each parallel feeder, then one of the fault in one of the feeder due to the presence of DG may impact the other feeder with the DG also. And hence we can conclude that any alteration in the fault current level at any point of the power system can influence the functioning of propulsion devices. The integration of DG units can potentially lead to various negative effects on protection devices, which can be categorized as follows. First one is reverse power flow. The second one is false tripping. The third one is binding of protection. And the fourth one is unwanted islanding. And the fifth one is unsynchronized reclosing. Now, let us focus on what is reverse power flow. We will take two parallel feeders with two DGs connected. Conventional distribution networks typically have a unilateral power flow from the transmission to distribution systems. The integration of DG units at the distribution level can change the direction of power flow depending on the size of the DG units. That means if the load connected to this feeder is less than the generation capacity, probably you can experience a power flow from the DG end to the main bus. In the given figure, excluding the fault and Y1 DG1, illustrate an example of reverse power flow. Without Y2 DG2, power flow from the grid to the loads on feeder 1 and 2. With DG2, the direction of power flow changes in part of feeder 2. The size of the DG2 should be sufficient to supply the power to the load on feeder 2. If the reverse current flowing through CB3 or fuse 3 goes beyond the current setting of CB3 or rated current of fuse 3, and hence CB3 / fuse 3 would operate, which is unacceptable. Similarly, we can experience false tripping due to distribution generations. We can also experience blinding of protections as we discussed, and we can also experience unwanted islanding due to DG. Due to short of time, we are not able to cover everything in detail. However, I request all the students to kindly go through the study materials for better understanding. Now, improvement of protection system in distribution network with DG units. Numerous strategies have been employed to minimize the influence of DG units on the power systems they integrate with. These approaches range from revamping protection systems to considering the capacity and specific attributes of the DG units. Broadly, these methods can be classified as disconnection of DG units, directional overcurrent protection, application of fault current limiters, limiting DG size, inverter control methods for inverter based DG units, application of distance protection, application of differential protection, artificial neural network and optimization methods, as well as few other methods. Thank you very much for your kind attention.